Okay, so we'll get started here, and so today we're going to talk about randomization tests, and we just watched that video from Mythbusters, okay, and I spent my whole own $2 to download it from Google Play. But anyway, if you got here late or you're watching on video at home, basically the premise was that the Mythbusters TV show, which is no longer on the air, they wanted to see if yawning is contagious. There's like spin-offs on Netflix now, though, right? It's like White Rabbit or something like that, or something. I don't know, whatever. Okay, but anyway, they got 50 participants. And each one was told to sit in this little room, and they were monitored on cameras. But before they went into the room, some of the people received a seed yawn. So Carrie yawned as she was putting them into the room, or they did not, and that would be the control group. And then Mythbusters recorded to see who yawned and who did not yawn. And so just a few things to remember and keep in mind is that our sample was not randomly selected, but the treatments were randomly assigned. So they did like a call for extras or something. And so this is not a random sample. These are people who, I guess, wanted to be extras or something. But the treatments were randomly assigned in the way that the assignment was systematic. They said 2 out of every 3 got a yawn, and one in every 3 was control. But the ordering of people was random. So who ends up getting control or treatment is random, right? Okay, so here it says 34 participants in the seed yawn group, and of those 10 people yawned. So 10 out of 34 is around 29%, 29.29412. And then 16 participants in the no seed yawn group. Out of that, 4 people yawned. Typo there. So 4 out of 16 is 25%. Okay. And then they kind of concluded. They said, "There's little doubt it does seem to be contagious." Okay. I don't know. What do you guys feel? You guys are shaking your heads. Okay. So here's just our data in a two-way table, okay? So we have either the seed yawn group or the control group, a total of 50 people, 34 over here and 16 over here, and these are our outcomes, yawn versus no yawn, okay?
Question?
Yes.
How did you get this data?
How? I just listened because, well, they said 25% and 29%, and then they said, what did they say? They said 2 out of 3 were in the thing. So just based on that information, I kind of tried to backtrack, and they said, well, I knew there was a total of 50, and if it was 1/3 and 2/3, then this seems to be kind of the most likely split. And if they said 25%, then it has to be this, and this 29%'s got to be this. So I just kind of worked it out that way, just based on. So the actual data, I don't know. I don't think any other combination of numbers is possible to get a total of 50 based on what they said in the video. But you know, if they were not truthful in the video, then all bets are off. But anyway, this is what we have, okay? And so like good statisticians, we might want to perform a hypothesis test, okay? So just symbolically, if I say Y is yawn and S is the seed group, meaning they Carrie yawned at them, they got a seed yawn before going into the observation room, and then C for control, meaning they got no yawn. Our null hypothesis is that yawning is not contagious, right? Meaning that the probability of yawning in the seed group minus the probability of yawning in the control group, that's going to be equal to 0. That whether you're in the seed group or the control group, the probability of yawning, there's no difference between those. Okay, so this is how we might express the null hypothesis here. And then the alternative hypothesis would be that yawning is contagious, meaning receiving a seed yawn makes it more likely for the person to yawn. Okay, and so symbolically, maybe I have to blow this up. We would write it this way: probability of yawning given that you're in the seed group minus the probability of yawning given that you're in the control group is greater than 0. Okay, and indicating that if you're in the seed yawn group, then your probability of yawning is greater than if you were in the control group. Okay, and so in our data, okay, to kind of indicate that this is coming from our data, we put our hats on this. Okay, and we have 10 over 34 minus 4 over 16, and this is a difference of around 4 percentage points. Okay, they said 29 versus 25%, so it's around you know, 4 percentage point difference. Okay, and the question is this difference significantly different from 0? Okay, that's what we want to know. Okay. Okay, and so the way this would work is we say, you know, if the null hypothesis is true, then we are saying that whether a person yawns or not is not related to whether the person got a seed yawn or not. Okay, so if the null hypothesis were true, whether they are in the seed group or the control group, the probability of yawning is just the probability of yawning. Okay, or so that means the results that we observed, this difference of 4 percentage points, is just a result of the random assignment of treatments. Okay, not that there's not something else related to whether someone yawns or not. Okay, and so what we can do is we can think of it as meaning 14 of these people, they were destined to yawn anyway. Okay, so out of the 50 people, 14 of them, they were just going to yawn, whether they got the seed yawn or they were in the control group. These people were just going to yawn anyway. It was their destiny to yawn. Okay, and so the fact that it ended up where 29% yawn in one group and 25% yawn in the other group, that must be just a result of the random assignment. Okay, and it has nothing to do with actually getting the seed yawn or being in the control group. It's just, if we just mixed up the groups, you know, it was just by random chance that 29% ended up over here and 25% ended up over there. Okay, and so, you know, when we do a hypothesis test, we want to calculate a p-value, and we would say, you know, the p-value is the probability of observing our data or something more extreme if the null hypothesis were true. Okay, and so what we observed in our data is a difference of 4.12 percentage points. Okay, one was 25%, the other one was 29.12 percentage percent. Okay, so we have a difference of 4.12 percentage points, but if the null hypothesis were true, we would expect the proportions to be the same for both groups, and we would expect that difference to be 0. We didn't get a difference of 0, we got a difference of 4 percentage points. And the question is that difference significant? And so our p-value is, what's the probability of getting a difference of 4 percentage points or more if random variation is the only source, if random assignment is the only source of variation. So the null hypothesis says random assignment is the only source of variation. So if that's truly the only source of variation, what's the probability of getting a difference of 4 percentage points or more? Okay, is that okay for setting up how to get our p-value? Okay, so before I go on, in your intro stats class, you might have learned about the chi-squared test, or maybe a 2-proportion z-test. Okay, and that's one way to kind of compare, you know, outcomes of categorical variables and things like that. I don't know if you guys remember, but the way it works for a chi-squared test is that there are distributional assumptions, and one of the conditions is that the expected counts for all combinations be greater than 5, right? So a lot of times, if you can use a parametric test, like, go ahead and use it. It's not that bad of a thing, but you have to make sure that the conditions to use that parametric test is okay. So here, what we get is the expected count in one of our cells is only 4.48, which is less than the kind of the minimum of 5. So this is not going to be a great example, okay, or not a good candidate to use the chi-squared test, okay. And then here's just some math for how I got that expected count. It's basically based on this. If being in the control group and being in the having yawning outcome, if they're independent, then you can say the probability is the joint probability is just the product, and then so you would do the total expected count in this cell would be 50 people total multiplied by probability of control times probability of yawn, and you do 50 times 16 over 50 times 14 over 50 and get 4.48. But anyway, this is just an aside to say we can't use the chi-squared test because this number is smaller than 5. Okay, so instead of a chi-squared test, what we will do is use a randomization test. Okay, and the randomization test has no distributional assumptions. Okay, but there is one assumption, and that is that there is exchangeability in the outcomes. Okay, so exchangeability in the outcomes. Let me just kind of talk about this. I should probably highlight like the Wikipedia articles for all of these things, but maybe I'll add links. So just in case you've forgotten the chi-squared test, you can go on Wikipedia, look up chi-squared test. You can look up exchangeability. You can look up randomization test. They're all kind of related. Okay. Exchangeability is the idea that under the null hypothesis, all possible permutations of the data are equally likely. Okay. Or that any permutation of the data is exchangeable with any other permutation of the data. Okay. So on a practical level, this means that exchangeability applies to experiments where random assignment has been used. So in our Mythbusters video, okay, who got the control or who got a CDON was a result of basically their order in the line, right? So if you had 50 people in a line, it would be like the first 2 get CDON, third person is control, okay? Persons 4 and 5, CDON, person 6 is control, okay? But, if we just imagine that the day was just a little bit different, the order of people standing in the line, that could have been mixed up, okay? The order of the 50 people in line could be mixed up, and so you would have another permutation of the data, and that would just be equally valid for kind of the data that we observed. Okay, so any arrangement of those people would change who got put into control and who got put into treatment. Okay, so and if we stuck with the null hypothesis, saying that 14 people were destined to yawn anyway, okay, then we would have the situation of exchangeability where the outcome of who yawns and who does not yawn, that could be shuffled up, and we could say, it just ends up being that a different group of 34 out of the 50 people end up in the treatment group, and a different group of 16 end up in the control group. Okay, so we're just saying all permutations, all arrangements of that line of 50 people are equally valid, and if we assume that 14 of those people were just destined to yawn, okay, then they would we would get different results, right? So so you could just imagine, I don't know, people carrying, that just a different arrangement of 14 people of the 50 people could have generated our data here, okay? All right. In the case where you do an observational study, okay, and you're looking at kind of two categorical variables and stuff like that, this idea of exchangeability is not valid, okay? We cannot assume that someone's gender or race is exchangeable with somebody else's gender or race or something like that, okay? And so observational studies generally you cannot assume exchangeability, but if the assignments, if the treatments are assigned randomly, you can generally assume exchangeability here. Okay, so this is a situation where we can assume exchangeability. Okay, so let me, I have all of the code written out here, but let me go ahead and I'm going to go ahead and just code this up, type this out for you guys in R. Okay. Let me magnify this here. Okay, so for yawning, I'm going to create a vector of 50 values. Okay, and I'm going to kind of just say true or false for whether they yawned or did not yawn. Okay, so I'm going to just say there were 10 people who yawned, and there were 24 people who did not yawn. So I'm using repeat. So I'm going to repeat the value true 10 times, and then repeat the value false 24 times. Then I'm going to repeat the value true 4 times, and repeat the value false 12 times. Okay, and so if I say we're going to take the first 34 values and put this in the treatment group, and then into the control group, we'll take the remaining 16 values. Okay. So that's what we have right here. Did I do something wrong? It's giving me all sorts of error messages. Okay, that seems okay. And then we can ask, all right, what is the proportion for the treatment group? And we have, 29.412 percentage points, okay? And then the mean of the control group, we have 25%, okay? And so our observed difference, is that what I call it? Yeah, observed difference is going to just be the difference between these two values. The mean of treatment minus the mean of control. And so our observed difference is about, I must have had a typo somewhere in my slides. Okay, about 4.4 percentage points, okay? 4 percentage points. And so this is what we observed, and the question is this difference of around 4 percentage points significantly different from 0, right? Or if the null hypothesis were true, how often do we get this difference or something more extreme? So, so what we're going to do now is we're going to let's assume that the null hypothesis is true. Okay. Then what we can say is that who gets assigned to group A and who got assigned to the treatment and who got assigned to the control is just a result of randomness. Okay. So just for reproducibility, I'm going to set the seed here, and I'm going to create a new vector. So right now, if I look at the yawning vector, okay, we have 50 values, and the first 10 are true, and the next 24 are false, and the next 4 are true, and the last 16 are false, or last 12 are false. Okay, what I'm going to do is I'm going to just shuffle this. Okay, so again, so it's kind of like taking that row of 50 people, the line of 50 people, and we're going to just shuffle up their arrangement. Okay, so I'm going to just do sample yawning. So I'm going to take this vector and I'm going to just mix it up. Okay, and so if I do this, I can take a look at randomized, and this is what it looks like. And now I'm just going to assign the first 34 people to group A, and the last 16 people to group B, okay? And so now we know who got put into group A and who got put into group B has nothing to do with anything. This is just a result of pure randomness, okay? There's no reason why group A or group B should have a higher proportion than the other than the fact that we just mixed up the order of people, and some people who have true will end up in one of the groups, and some people who have true will end up in the other group, okay? So, so I'll go ahead and do this, and we can just take a look at what group A looks like. Group A looks like this, and group B looks like that, and we can just ask, what is the mean of group A, and what is the mean of group B? So this will give me the proportion in group A, and I get 23.5% versus 37.5%. Okay, and I think so. This is what I am to get. So group A, this would be kind of the analog to the treatment group, and group B would be the analog of the control group. Okay, but they're just results of pure random chance. There's nothing going on other than the randomization process. Okay, and so we could say, well, what kind of simulated difference do we get? And so the difference here, we got a difference of around negative 14 percentage points. Okay, so that's just from randomness. Group B had 14 percentage points more people who yawned than group A. So in that would be like 14 percentage people in the control group more yawned than the people in the treatment group. Okay, so that would obviously not support the argument of Mythbusters, but this, again, keep in mind, this was just a result of randomness, okay? And so if we did this again, we could do this a whole bunch of times. So I think I did this 5,000 times, okay? And the process is the same every single time. So I'm gonna create, so I'm gonna just set seed once to 1, just for reproducibility, okay? And I'm going to create a vector of differences. I'm going to do this 5,000 times, and I'm going to say for I in 1 through 5,000, basically I want to just do this exact same process, okay? Every single time I'm going to just take my sample yawning, and I'm going to shuffle it up. I'm going to just shuffle up the order of those 50 people, and I'm going to just say, the first 34 go into group A, the other 16 go into group B, okay? And so we know there's no reason why group A or group B should have higher proportion than the other than the randomization process. That's the only source of the variation that we see. And then, and we're gonna keep track of all of these differences, okay? So I'm gonna just say, here are my differences. So into the differences vector, into spot I, I'm going to take the difference between the proportion of group A minus the proportion of group B. Okay, so we're going to just see what kind of values do I see when I mix this up. Is that okay? And so this is going to produce kind of a sampling distribution of the different differences we see between proportion A and proportion B. Okay. Or group A and differences of proportions. Okay. right, so there's no, again, no distributional assumptions. We're just assuming this exchangeability is valid, okay? And if exchangeability is valid, then this step of shuffling up our yawning vector is valid, okay? If it's not, then this step is illegal, okay? And then we go ahead and we do that, and we'll just kind of take a look at what kind of values we see. Let me just, yep, okay, so because I set the seed, I got the same values as I did before. And so what we see is that the average difference between the proportion of those in the treatment group who yawned and the proportion of those in the control group who yawned, that average difference, that mean, is around 0, okay, which is what we would expect. But take a look at that median. That median difference is 4.4 percentage points, which is exactly what we observed, right? So we observed a difference of 0.44117, which rounds up to 0.44118. So this is the median difference. And so if we go back, okay, remember the p-value is, you know, what's the probability of getting a difference, so this should say 4412, okay? What's the probability of getting our observed difference or something more extreme, okay? We want to know, okay, well, how often do we get this value? So I'm going to take, I can take a look at the histogram of my differences. All right, maybe, and we see, it might, maybe, I don't know if you guys can see this, it's almost like an optical illusion, but there's actually gaps here. There's gaps going on, okay? And I'll explain that in a moment here. But what we can do is we can just ask, okay, well, how often, so I have 5,000 of these differences that we observed, and we can just say, well, how often were our differences greater than or equal to our observed difference? Okay, so this is what we have. So what I can just do is I can ask the mean of this, right? So I can just take the mean of this vector, and it says that happened about over 50% of the time. Okay, over 50% of the time, when I shuffled up my my vector of 50 people, over half the time, I got a difference of 4.4 percentage points or more, okay? So basically what that tells me is that when Mythbusters gathered their data, they just got a lucky coin flip, okay? If they did it another day, they might have gotten a smaller difference. If they did it another day, they might have gotten another difference. They happened to get this difference of 4 percentage points, which they said is enough to convince them. I think, you know, they said, well, the difference isn't dramatic, but because the sample size was so large, it seems to confirm whatever, you know, we saw, right? But that difference of 4 percentage points, where the treatment group yawned more than the, yawned 4 percentage points more than the control group, that happens like half the time just from random assignment, okay? So it does not convince us that, at least with the way their experiment is set up, that there's any kind of relationship between their seed yawn and whether someone yawned in that room, okay? And it turns out that if you actually took the absolute value of the differences, and if you sort the absolute value of the differences, okay, let's just look at like the first 5. It is literally the smallest possible difference that could have resulted, okay? And the reason why we see these gaps here is because there is 16 people go into one group and 34 go into the other group. So right now we have 10 versus 34 minus 4 versus 16, and that gives us a difference of 4 percentage points. If I just changed it ever so slightly, right, to say 11 in one group and 3 in the other, because we have a total of 14 people who yawn, then that would give me a difference of 13 percentage points. If I try altering it the other way, saying a difference of 9 versus 9 in the treatment group and 5 in the control group, okay, then that difference ends up being negative 0.0477, okay? So it's just not possible to get a difference smaller than 4 percentage points, okay? Just because, and so if I altered this to 8 and 16 or something, now we have a difference of around 14 percentage points, but in the wrong direction, okay? And so that's why we're getting these gaps here, because there's no arrangement of these 14 people that will give us a difference of like 8% or 7% or something like that, okay? So that's what we're seeing. And basically, we got, you know, we just happen to be on the positive side, or that difference is 4 percentage points or higher. And that's going to just happen half the time by random chance. It's not actually indicative that there is a difference. Okay, and so so I've written the code up in the notes. Okay, basically this is just one randomization, and the randomization test basically just repeats this randomization process. So you're building up the sampling distribution by doing this many times, and then you calculate your empirical p-value by saying how often does how often did my random differences produce a difference as great equal to or more extreme than what my data produced. Okay, so my data produced a difference of around 4.4 percentage points, and my randomized difference that happens over 50% of the time. So there's a decent or high probability that the difference that Mythbusters observed is just from random chance alone. Okay. If for whatever reason they had a different question, okay, so I should probably write this out. But if they said, does not necessarily is yawning contagious in that it increases the probability of yawning, but just does seeing someone yawn affect someone else's yawning? Okay, so maybe somebody might say maybe it increases, maybe it decreases, right? So seeing the yawn, does that produce a change? Well, in that case, you would have a two-sided test, right? And you would have to look at the absolute value of the differences. And in that case, all 100% of the randomized differences that we observed is greater than or equal to the observed difference that we have. Okay, so we have a p-value of 1, which almost never happens, but in this case it does, right? It's kind of just like someone flipping the coin 10 times and they get 5 heads and 5 tails, and then they say, well, now do I have evidence that the coin is unfair? Well, if we did any other test, 100% of them would end up with values like ours or something more extreme. So this would not convince us. Okay, our empirical p-value. Why do I call this an empirical p-value and not just a regular theoretic p-value? It's not based on the distribution. It's based on randomized differences, right? And so if you ran this on your computer with a different seed, okay, or you didn't set the seed or whatever, your 5,000 randomized differences will be, ever so slightly different from mine, right? So if I just did this again, and if I said seed to 12 or something like that, okay, and I calculate mean of differences greater than or equal to the observed difference, okay, I get something a little bit different than 0.504, right? And if I just did this again, I get something a little bit different. So this p-value of 0.504 is just based on my 5,000 randomizations, and I would probably need to do a lot more. But again, these are just going to be we're going to get something slightly different. We're going to get everything kind of in the same realm of around 50% or something a little bit more than that, but it's going to be empirical. If you want an exact p-value, it is possible, okay? And I'll just include the link to a Wikipedia article here for Fisher's exact test, okay? So what Fisher's exact test does is it literally calculates every single possible permutation of, you know, the 50 people in your line. There's a lot of permutations, but there is a finite number of possible permutations. And Fisher's exact test, if your computer can afford the computation for these giant factorials, Fisher's exact test will give you the exact p-value based on the exact permutations, okay? And so, so other names of this randomization test also goes by, so there's Fisher's exact test, which is the exact thing. Randomization test usually just involves the computer doing the random sampling for us or random assignment for us. But then, you know, something you might hear, the permutation test, which is a little bit ambiguous in that you're not quite sure if you're talking about the computer doing random permutations or if you're doing actual permutation calculations based on Fisher's formula and stuff like that. Okay. That's it for the randomization test. Are there any questions on this? Yes.
If you are to do this like 5,000 times, don't we know that it will converge to a normal distribution?
We don't. If my data were a little bit more extreme, it might not be normal. So if rather than having kind of 4 true, like if my data only had like, I think like 2 and 12 or something. Let me just see. Well, that one's also normal looking. So we would, so the central limit theorem applies when your expected counts generally are 5 or more. I guess if instead of, I think maybe if I did this, 4 and 28 or something, if I change the proportions to change the proportions something different, we would get something not necessarily normally distributed. Let me just change this around here. Okay, let's just go ahead. Error in valid number of breaks. I'm getting a bunch of NAs. This is no good. Okay, I have to figure out what I'm doing wrong here. The answer is the central limit theorem does not always apply. And that's why the chi-square test has these kind of conditions that must be met for the distributional assumptions, which even though it's not apparent, the chi-square test does rely on the central limit theorem underlying certain things. So there are certain conditions and situations where it doesn't apply. And the randomization test basically has no distributional assumptions, whereas you know, we often see things that look normal, but it's not guaranteed to always look normal. So, okay. All right, we'll just end a couple of minutes early, and we'll see you guys on Wednesday. We'll start talking bootstrap and other types of resampling methods.
回答。